Hello and welcome. In today's video, we'll be diving into an important concept in data structures and algorithms, the heap priority queues. If you ever wondered how operating systems optimizing tasks and how search engines manage billions of results efficiently, then this is the topic for you. We will explore what priority queues are, how they work, and role heaps play in implementing them. Whether you are working on a job scheduling, graph algorithms, or even real-time systems, understanding heaps-based priority queues is key to solving many computational problems efficiently. By the end of the video, you will have a solid understanding of heap priority queues and their applications along with a breakdown of their time complexity. So let's get started. So what is a priority queue? Let's start by understanding what is a priority queue is. A priority queue is a data structure where each element is assigned a priority. Elements with higher priority are dequeued before elements with lower priority, regardless of their insertion order. Think of it as a waiting line where people are sorted by urgency. For example, in a hospital, the most critical patients are treated first, not based on when they arrived, but based on the severity of their condition. They make priority queues ideal for scheduling tasks or managing events. Applications of priority queues. Priority queues are widely used in several real-world applications. One of the most notable examples is in job scheduling, in operation systems. In these systems, tasks with higher priority like system updates or critical process are given precedence over normal tasks. Another application is Dijkstra algorithm for finding the shortest path in a graph, where the priority queues is used to process nodes in order of their distance from the source. Huffman coding for the data compression also uses a priority queue to build the optimal binary tree. These applications show how priority queues are essential for efficient tasks management and problem solving. So what is a heap? Now let's dive into what a heap is. A heap is a special type of binary tree that satisfies the heap property. In a max heap, the value of each node is greater than or equal to value of its children, making the root node the largest. In min heap, the value of each node is less than or equal to its children, making the root node the smallest heap are completely binary tree, meaning all levels are fully filled, except possibly the last which is filled from left to right. Now that we know what a heap is, let's see how heaps are used to implement priority queues. In a priority queue implemented with a heap, the root always falls the highest or lowest, depending on max min heap. Priority elements. Insertion of a new element takes place at the next available spot in the tree, and then we heapify the tree to maintain the heap priority. Removing the elements dequeue operation always removes the root, and we replace it with the last element in the heap. Then we heapify the tree to restore the heap priority. The operations insertion deletion are efficient with heaps because they take O bracket log n time. Okay, now let's do an example in a binary tree. So now we are going to explore how heap operations work using a min heap binary tree. Min heap is special type of binary tree where the root node is always the smallest element and each present node is smaller than its children. Let's start by looking at our initial binary tree. In this tree, the root node is 5, which is the smallest value, and it follows the min heap property, where every parent node is less than its children. Now let's perform some operations on this heap, starting with inserting a new element. Suppose we want to insert the value 2 into the tree. When we insert 2, it will initially be placed as the left child of 12. The tree will temporarily look like this. At this point, the min heap property is violated because 2 is the smallest than its parent, 12. To fix this, we perform a heapify up operation. We compare 2 with its parent 12, and since the 2 is smaller, we swap them. The tree now looks like this. Next we compare 2 with its new parent 10. Since 2 is smaller, we swap them again. Finally we compare 2 with the root node 5. Since 2 is smaller, we swap them as well. And our tree now looks like this. Now the tree is valid min heap again, with 2 as the root. Next let's move on to the pole operation, which means removing the root node. Since the root of a min heap is always the smallest value, we will remove 2. To do this, we replace 2 with the last node in the tree, which is 12. After removing 2, the tree temporarily looks like this. To restore the heap property, we perform a heapify down operation. We start by comparing 12 with its children 5 and 20. Since 5 is the smallest, we swap 12 and 5. Next we compare 12 with its new children 10 and 18. Since 10 is the smallest child, we swap 12 and 10. 3 is restored as valid min heap with 5 as the root. Finally let's look at the peak operation. Peaking simplify means looking at the root value without removing it after polling. The root of the heap is 5. So when we peak, we see the 5 is the smallest value in the heap. Now I have written a code for you in Java. Let's begin by understanding the constructors and variables we initialize. The heap with a given capacity. We define 3 variables: heap, size, capacity. The heap is for store the elements of the min heap. Size keeps track of the current numbers of elements in the heap. Capacity specifies the maximum number of elements that heap can hold. Next we have methods to find the indices of parents and children of a node in 16 line to 28 line. The parent method calculates the index of parent of a given node. Similarly, left child and right child returns the indices of the left and right children respectively. These indices follow the rules of complete binary tree, where left child 2 multiply index plus 1, right child equal 2 multiply index plus 2, parent equal index minus 1 divided by 2. The swap method. In line 31 to 34, the swap method simplifies swaps the elements at indices I and j in the heap array. Now the inserted method. Line 38 to 53. The insert method inserts the new value at the end of the heap. Then we check if the heap property is violated, meaning if the current element is smaller than its parent. If this happens, we swap the elements and continue checking until the heap property is satisfied. This process is called heapify up. Now the extract min method. It removes and returns the minimum elements, which is always at the root. It's in the line 56 to 73. First we store the root, the minimum element, in the variable min. We then replace the root with the last element in the heap and decrease the size. After that, we call heapify to restore the heap property by moving the new root downwards, ensuring the smallest element remains at the root. Now let's move on to the heapify method. This method is used to restore the heap property after the root is changes. It's in the line 76 to 96. Here we compare the current node with its left and right child. If either the child is smaller than the current node, we swap the values. Then we recursively call heapify to ensure the heap property is maintained throughout the tree. Now let's move on to the peak method. The peak method allows to see minimum elements without removing it from the heap. It's in the line 99 to 105. It simplifies returns the root element of heap, which is the minimum element. Now the print method. The print method prints the elements of the heap. It's in the line 108 to 110. Finally, we have the main method to test the functionalities of our min heap. It's in the line 130 to 136. In this, we create a new heap with a capacity of 10 and insert several elements. After inserting, we print the heap peak at the minimum element, extract the minimum element and print the heap again after extraction. And you can see the output. Now let's talk about applications of heap priority queues. A heap priority queue is primarily used in situations where elements needed to be proceeded based on their property, with the highest priority element being accessed first. Commonly, applications include CPU scheduling, graph algorithms, event-driven simulations, data compression, and stock market order matching. Now let's look into the time complexity table. Insertion and deletion are O bracket log n because we need to maintain the heap property, which requires rebalancing the tree. However, peaking at the highest priority element is O bracket 1 since it's always at the root. Building a heap from an unsorted array can be done in 0 n time. To sum up, today we have learned about heap-based priority queues and how they are crucial for efficient managing tasks with varying properties. We explored the heap structure, its properties, and how it supports priority queues operations like insertion and deletion. We also saw practical applications in job scheduling, graph algorithms, and real-time systems. Understanding heap priority queues is not just useful for academic but also for real-world applications where performance and efficiency matter. With the knowledge of time complexity and how heaps work, you will be better equipped to implement and optimize priority queues operations in your projects. Thanks for watching. Hope you all got an idea about heap priority queues. Don't forget to like, subscribe, and stay tuned for more content. See you in my next video.